Hello guys, welcome back to my channel. Today we're going to be looking at question 3 on the 2019 CXC Cape Pure Mathematics past paper 2. Alright, now this paper is turned sideways, so I'm going to actually rewrite the question so we can clearly see it. So it says 5 sec theta minus 2 sec square theta is equal to tan square theta minus 1. Alright, and we're supposed to solve the equation where theta is greater than or equal to minus pi, but is less than or equal to positive pi. Alright, let's get right into it. So the first thing about this question is that we have, it seems like a hidden quadratic. As you can see, we see the square terms and we see the non-square term. But here's the problem. We have sec squared and we have tan. Now, of course, we can't have both ratios. One of them have to change. Now, which one do we change? Now, of course, since we have a sec, that is going to have to remain. So it means that the tan squared theta has to go away. Now let's recall some identities here. So recall that 1 plus tan squared theta is equivalent to sec squared theta. So we have to know some of these identities, right? So technically speaking, we can say that tan squared theta is equal to sec squared theta minus 1. Right, good. So I'm going to have 5 sec theta minus 2 sec squared theta equal to sec squared theta minus 1, and then you put the minus 1 that was there. Once you realize that it's a hidden quadratic, we're now going to bring everything to one side. Now, let us decide this. We might want to keep the sec squared positive, so we could bring over the 2. Alright, so it's going to come over as a 2 sec squared theta. You have sec squared theta over there already, so plus sec squared theta. We're bringing everything to the right. Alright, the 5 sec theta comes over as a minus 5 sec theta. And of course, minus 1 is going to give me minus 2. Of course, it's all equal to 0. So we have 2 sec squared theta. Well, this is going to be 3 of them. 3 sec squared theta minus 5 sec theta minus 2 equals 0. At this moment, you have two options. You can treat this as how you normally treat a hidden quadratic, which means I could make a substitution for sec theta. However, in the interest of time, I don't need to do that. I can solve it as it is. I'm just going to think of the variable sec theta, like how I would normally think of x, and sec squared theta, like how I would normally think of x squared. So I'm going to go with the AC method. 3 times negative 2 is negative 6. Now, what two numbers do I multiply to give me negative 6? When I add them, I get negative 5. I could use negative 6 and positive 1. So I'm going to have 3 sec squared theta minus 6 sec theta. Bear in mind that sec theta is a variable like x, plus sec theta minus 2 equal to 0. Alright, good so far. Please take it in. Let me just scroll down a bit so I can have some more space. So here now I can say that I can factor out a 3 sec theta, because remember you pair them off. 3 sec theta, and I'm going to have sec theta minus 2. Here, the only thing you can take out is 1. You have sec theta minus 2, and everything is equal to 0. Alright, so it's either 3 sec theta plus 1 equals 0, or sec theta minus 2 equals 0. Now, in this case, we can say that sec theta is equal to negative 1/3. And here we can say that sec theta is equal to 2. Now, of course, we're not familiar with sec. We're familiar with sec, but it's easier to work with a different ratio that is related to, the common ratios, sine, cos, and tan. But recall that sec is really 1 over cos. So if sec theta is equal to negative 1/3, cos theta would be the reciprocal, which would be negative 3. Alright? Or over here, you're going to have cos theta equal to 1/2. Now, you have a very big problem on this side, because cos theta is between positive 1 and negative 1. So this is not applicable. This can't be solved. Alright? Then you have cos theta equal 1/2. Now, in this case, we can actually go for our triangle to see what would happen in this case. Alright, let's go. I'm going to draw my 60/30 triangle. All right. In other words, this is in radians now. Of course, they ask you for your answer in radians. So in radians, on my right angle triangle, of course, you know the whole 60/30. You can start with an equilateral triangle and break it down. Or you can choose to remember it. This down here would be pi over 3. And of course, this up here would be pi over 6. This is root 3. This is 1. And this is 2. So when you have cos theta equal a half, I'm going to go for the smallest angle here, which is alpha. Alpha would be equal to, as you can see here, we have pi over 3, which in other words is 60. Let me write it bigger. So this is pi over 3. So alpha is equal to pi over 3. Now, bear in mind, we are ranging from negative pi to positive pi. So I can go for my unit circle. And now this is cos positive a half. Bear in mind that cos is positive in 2 quadrants. First quadrant, so you're going to have pi over 3 here. Is also, so remember, all science teachers crazy, is also going to be positive in the 4th quadrant, which means you're going to have a pi over 3 here. Now, of course, based on the range, bear in mind that at this point you have pi. You can't pass pi and you can't pass minus pi, but you can go clockwise and you can go anti-clockwise. All right, I'm writing all over the paper here. Now, if I go clockwise, I'm going to have to stop here, which is pi over 3. So theta would be equal to pi over 3. We can also go anti-clockwise because it goes from minus pi. If I go anti-clockwise, as you can see here, it would be minus pi over 3. And those would be my 2 responses for this particular question, all right? Based on the fact that the range is limited between negative pi and pi, it means that you can't have any other answers, all right? So that would be it. All right, we get into question B. It says, let f of x equal cos x plus 2 sin x. Express f of x in the form r sin x plus alpha, where alpha is acute. Now, by just looking at this question, there are certain things we want to point out. Please note that you cannot distribute this bracket because this is not multiplication. This is sign off. It's a single function. And by looking at the function like this, there's only one thing that should pop in your mind right away, and that is the compound angle formula. Now, if we're going to express this in this form, we're going to have to start by assuming that the two must be equivalent. So what we're saying is that cos x plus 2 sin x must be equivalent to r sin x plus alpha. Now, of course, we can't compare two things that are in different forms. So clearly, I'm going to have to apply my compound angle formula on the right here to expand that. So let me just say here that this is going to become r. When you have sine x plus alpha, you're going to get sine x cos alpha plus r sine alpha cos x. All right. So you have to know the compound angle formula. Now, at this point, what we're going to do is that we're going to compare coefficient. All right. Compare coefficient. So we're going to look at what is multiplying cos x on the left, which clearly we see is 1. On the right, we look for cos x, which is over here, and what is multiplying cos x is r sine alpha. All right, good. Let's move on to sin x. On the left, you have 2 multiplying sin x, that's the coefficient of sin x, but on the right, even though you have the sin x in the middle, you have r and cos alpha multiplying it. So you're going to have r cos alpha. All right, so you can say that sine alpha is equal to 1 over r, and we can say that cos alpha is equal to 2 over r. Now at this point we can make our lives a bit easier by simply drawing a right angle triangle. Alright, so in this case I'm gonna have, let me put in my right angle triangle. If I were to put, let me put the angle here. If I were to put alpha here, we know that sine alpha is opposite over hypotenuse, so this would be 1, this would automatically be r. Then cos is adjacent, so it would be 2 over r. So let's talk about a few things. We can start by finding r, which is using Pythagoras' theorem, the square root of 1 squared plus 2 squared, which makes r equal to root 5, as you can see right away. Good. We also need to find the value for alpha. Okay, so let's see what happens here. Let me just go over here so we can keep it going. All right, from this triangle, we have the opposite side and we have the adjacent side, which tells me that I can talk about tan alpha, which is opposite over adjacent, 1 over 2. All right, good so far. Now, of course, from all of my triangles, I know that I'm not going to get a half when it comes to tan. So what I'm going to do here is that I'm simply going to pull up my calculator, because alpha is going to be tan inverse of a half. And I'm going to take that in radians. So let me pull up my calculator here. All right, let me make this a bit larger so we can all see it. All right, so it says we have it in degrees and we need it in radians. So it's going to be on shift mode. Radians is 4, as you can see. So I'm going to press 4 there. So I now have it in radians. So I'm going to shift tan, and I'm dealing with a half here. So 1 over 2. Close bracket, equal. So we have 0.464. Remember, it's 3 significant figures. So that's 0.464. Let me put this back down here. So alpha is equal to 0.464 rads. Of course, we know it must be to 3 significant figures unless otherwise stated. So that is what we have to put it as. So f is now going to be equal to, so we're going to come back to the form. We found r, which is root 5, so I'm going to have root 5 sine of x plus alpha, which is 0.464. So you actually have the function in the form that you wanted. This is the form that we wanted. Right, scroll down and see what they have in store for us. For my next question, it says, hence or otherwise, find the general solution of the equation. Now, of course, we're not going to be using this form. That's one of the reasons why we found the equivalent form. So we're going to be using f equal root 5 sine of x plus 0.464. So we're actually going back to where we started, the equivalent form. So instead of using this equal to 0, we're going to be using its equivalent form equal to 0. So what do I say? I'm going to say this implies that root 5 sine of x plus 0.464 is equal to 0. We transpose it like a normal equation, as you know. Alright, so I'm going to have to start by getting rid of the root 5. So you normally get rid of the coefficient before you get to the function. So I'm going to have sine of x plus 0.464 is equal to 0, as we would have divided both sides by root 5. Now, we want the general solution. Good? So in order to get the general solution, let me recall what the general solution for sine is. And let me use a different color. For sine, the general solution is theta equal n pi plus negative 1 to the n times alpha. This is a general solution. Good. Now, how do I get alpha? Now, everything in here is naturally going to represent my theta. All right, so follow me carefully now. I can say from this, my alpha value is equal to the sine inverse of 0. And of course, we know that sine inverse 0 is actually going to give us 0. So alpha is 0. All right. So my theta value, which is n pi plus negative 1 to the n times alpha, which what it means is that inside of this formula, alpha is going to be 0. And of course, theta is going to be whatever is here, which is x plus 0.464. So let me go down and put all of this together now. Oh, I need some more space here. All right, so let me just break this into 2 parts. So at this moment, what I'm going to say is that x plus 0.464 is equal to n pi. All right, and then we don't need to put the negative 1 to the n times alpha, because if alpha is 0, all of this is 0. All right, so we can simply go ahead and say that this implies, bear in mind your task is to find x. So x would simply be equal to n pi minus 0.464. And of course, remember that there are 3 general solutions, one for sine, one for cos, and one for tan. You have to know all of them. All right, state this down some more. Determine the minimum value of the function. All right, good. Now here's an easy way. I'm going to give you a very easy way to work this out. Now the function f of x, as you know, let me write it back here. F, all right. Now, how does the sine function work? Whatever, if you have, let's say a sine x. All right, we know that sine x by itself, the maximum value is 1, the minimum value is -1. Whenever a value goes in front of the sine x, like 2, the maximum value becomes 2, the minimum value becomes -2. Any value that goes in front of the sine x, that is applicable to it. And of course, in transformation of graphs, you can know that concept from there. So as it is, the f function, the value in front of the sine is √5. So it means that this is greater than or equal to -√5, but it's less than or equal to +√5. That is what we know about it. Now we can build this function up to what we have here. Now it means that the minimum value of the function is -√5 and the maximum value is +√5. Now how am I going to build this function right here? I'm going to have to start with the function down here. Now look what happens. It says the first thing we're going to do to the function is negate it. Alright? Now what happens when you negate the function? When you negate a function, of course, if this side was greater, it becomes less, and if this side was less, it becomes greater. So I'm going to negate the function. So negative f means we negate both sides. I'm going to have, this is going to become a +√5, and this is going to become a -√5 over here. Now, what happens? The signs are going to turn around. That is what happens when we negate the function. Now, of course, we're going to bring in the 2, so we're going to add 2 to both sides. So I'm going to have 2 plus √5 is greater than or equal. And when you add something, it doesn't affect the signs, right? So we can either put +2 plus -√5, or we can simply write 2 minus f. Good? Is greater than or equal to 2 minus √5. All right. What's the next thing we need to do? We need to invert it so we can get it down. Now, whenever we invert the function now, that is when the signs change again. All right? It's because the function becomes inverted, so the maximum value now turns to be the minimum, and the minimum turns to be the maximum. And let me help you to understand conceptually. This function would have a minimum turning point. This function would have a maximum turning point. When you flip it, this minimum turning point goes up and become maximum, and this maximum comes down and become minimum. That's what we mean by flip, because that is literally what will happen to the function. All right, so the signs are going to change. So I'm going to have 1 over 2 minus f. The sign turns around, 2 plus root f, but is less than or equal to 1. Well, this is 1 over, my bad. 1 over 2 minus root f. All right, let's take this down. √5, sorry. Now, of course, you know that you have 2 up there, so you're going to have to multiply by 2. So we multiply all parts by 2. So I'm going to have 2 over 2 plus √5 is less than or equal to 2 over 2 minus f, which is less than or equal to 2 over 2 minus √5. Good. Now, the simple question is, what is the minimum value? Of course, the minimum value would be the value down here. So we can say that the minimum value would be 2 over 2 plus √5. That's my minimum value here. All right, we can build it up like that. That's one good way to work it. You can go wrong when you build it up like that. All right. Now I'm at question C. All right, let's see what happens. And this is a proof question. It says, prove that the tangent of a plus b minus tan a is equivalent to this. Now, of course, in carrying out a proof, I need to determine, first of all, which side am I taking. And it looks to me that it's best to take the left-hand side here. So I'm going to write a statement that says taking the left-hand side, LHS, as we know it. All right, let's go. Now, of course, based on what we see here, we're going to have to apply the compound angle formula for tan. But let me start by rewriting it. I have the tangent of A plus B minus the tangent of A. All right? Applying the compound angle formula here, I'm going to have the tangent of A plus the tangent of B all over 1 minus tangent A tangent B. Alright, minus the tangent of A. Alright, good. Good so far. Now the question is, what am I gonna do with this? Now, if I look on the right hand side, I realize that I'm seeing sine cos, which tells me that the smart thing to do here is to change the different things to sine and cos functions. Alright, let's take this down. So we're gonna need some space here. Now, we know by now that tan is really sine A over cos A. Alright, we should all know that. So we're going to have sine A over the cosine of A plus sine B over the cosine of B all over 1 minus sine A over cosine A times sine B over cosine B. And all this is going to subtract sine A over cosine A. Let's fix this up. Now, clearly we have fractions. So normally when you have fractions, you find the LCM and you break them down. And that is exactly what I'm going to do here. So in my numerator, my LCM will be cos A, cos B. Alright, of course, cos A into this will be cos B. So I'm going to have sine A, cos B, plus cos B into this is going to be cos A. So I'm going to have cos A, sine B. Alright, now this should start looking familiar to you, alright, because right there we have an identity. Alright, all this, and if you don't want to put it back over it, what I can go, well, let me just draw a different color line now. So let me just use a line here. This is gonna become 1 minus sine A sine B over cos A cos B. Please remember that you still have the sine of A over cosine of A. Alright, what do I do next? For me to simplify this, I need the denominator to become a single fraction. So I'm going to put a 1 there. So I'm going to leave my numerator alone. Alright, I'm just going to rewrite it. So I'm going to have sine A cosine B plus cosine A sine B all over cos A cos B over, of course, the LCM for this down here is going to be cos A cos B, right? Cos A cos B. Now, 1 into cos A cos B is just going to be cos A cos B. Cos A cos B into cos A cos B is 1. So it becomes minus sine A sine B. And of course, all this minus sine A over cosine A. Now let's go. We can go back now and glimpse at what they want answer to look like. Now clearly, you have sine B over the cosine of A times the cosine of A cosine B. Alright. Let's tidy this thing up. Now, what happens when you divide fractions, alright? You multiply by the reciprocal. So I'm going to multiply this by the reciprocal of this right here. So let me get the smaller. So I'm going to have sine A cosine B plus cosine A sine B all over cosine of A cosine of B multiply by the reciprocal of all this down here. So you're going to have cos A cos B all over cos A cos B minus sine A sine B. Alright, I'm going all the way over here now. Minus sine A over the cosine of A. Now see what is going to happen here. Let me get a different color in now. This into this is 1. This into this is 1. Let's start fixing up a few things right here before I go any further. Now clearly in my numerator, sine A cos B, that's a double angle formula. That's a compound angle formula for sine. And down here is a compound angle formula for cos. So let me go ahead and fix that up. So up top, and let me see if that's what they want. Up here, right? So it's always good to glimpse what your answer should be. So you have sine B all over this. All right, okay. All right, now, since we know that they want the cos A, cos B, which is the compound angle formula for cosine, let me start by putting that in. So this is going to be the cosine of A plus B. All right, that can go right there because we know they want that. In the numerator, you have sine A cos B. Let me put that back. Sine A cos B plus cos A sine B. And of course, all this minus sine A over the cosine of A. All right, once again, we have a next fraction. We can go right ahead with the LCM. The LCM would be these two right here. So I'm going to have cosine of A plus B times cosine of A. All right, this into this is cosine A. So cosine A is going to multiply everything up here. So what I'm going to have here is the let me just put it here for now. Cosine A, sine of A, cosine B plus cosine A, sine B minus sine A times cos of A plus B. Right. Let's make some sense out of this now. Okay, so the denominator is okay. It is the numerator that I need to work on. All right. Let me write this properly right here. So this is sine A times the cosine. All right, good. Let me take it over to this side now. Clearly, if I'm going to simplify this, I'm going to have to re-expand this. All right. So I'm going to have, if I expand the top there, I'm going to have cos A, sine A, cos B, plus cos A times this is going to give me cos squared A sine B. Good. Let me create some space here. Clearly, for this to work out, I also need to expand this. So I'm going to have minus I'm going to have sine A, and then in bracket, if I expand that, I'm going to have cos A cos B minus sine A sine B. All right, all over this. So you have the cosine of A plus B times the cosine of A. Good. Start this up now. So I'm going to have cos A sine A cos B plus cos squared A sine B minus. All right, so now this sine A is going to multiply this. So I'm going to have minus sine A cos A cos B. All right, and then negative times negative is positive. So I'm going to have plus sine A times sine A sine squared A sine B. All over the cosine of A plus B times the cosine of A. Now look out for things that can cancel out. So for instance, all of this would take out all of this right here. So that's gone. All right, what else can I do? I'm going to group these two. So I have cos squared A sine B plus sine squared A sine B, which tells me that right away that sine B is common. So I'm going to factor out a sine B. In bracket, I'm going to have cos squared A plus sine squared A all over cos of A plus B times the cosine of A. Alright, now of course all this in bracket is equal to 1, so you can write a statement there stating that it's equal to 1. But I'm out of space, so I'm just going to put in the answer here. So I'm going to end up with a sine B. Scroll down a bit. All over cosine of A plus B cos A, QED. And that's it.